Hope everybody's doing well and okay for one more talk before lunch. But like Fadil said, I want to talk about evaluation and uncertainty in the age of robot learning. Fadil already gave a great introduction. Quick overview of who I am. I'm really interested in uncertainty-aware machine learning models, specifically towards systems that will eventually be deployed in human environments. I did my PhD at the Stanford Intelligent Systems Lab, focusing on a lot of autonomous driving, thinking about environment prediction, occlusion inference, and then eventually uncertainty-aware trajectory prediction, which actually led me to my current role at TRI. I work as a research lead for Trustworthy Learning Under Uncertainty, short acronym is TLU, and we co-lead this team with Dr. Haruki Nishimura. Our focuses are visually displayed here, but I will talk a lot more about them shortly. And with that, let's talk about robot learning for a second. We've seen some really cool things in this space, right? We've seen things come out of Pi, NVIDIA, TRI put out some stuff a couple years ago. There are really great capabilities out there right now that honestly I didn't feel like were possible 5-10 years ago. And that's really exciting. That is encompassed in this theme of what you can call large behavior models, LBMs. They're also known as vision language models, VLAs, and embodied foundation models, EFMs. These are all synonyms, more or less. All these models, they scale and they create these extremely dexterous, generalizable behaviors, which is super exciting. That being said, they still fail. Here are a couple examples. Some of these are from Pi and some of these are from TRI. The bottom ones are from TRI. Yeah, things go wrong. This one with the coffee spill on the bottom right, I enjoy that one a lot because, yeah, robot could really get damaged if it gets into liquid. So that could be not so great. So this is what sort of motivates our team. What we focus on is threefold. It's policy evaluation, failure detection mitigation, and active learning. All these three things are thinking about uncertainty. The policy evaluation bit is how do we characterize successes and failures? How do we put guarantees on that? Failure detection mitigation is thinking about how can we find the failures fast and then hopefully recover gracefully. And lastly, active learning is thinking about uncertainty in a positive light, right? It doesn't always have to be about failure and safety and all these bad things. It can be about learning and adapting. And so that's the idea. Hopefully we can learn from these failures and actually become more robust and more generalizable down the line. None of this is possible without robot data at scale. So I've also been involved in some data scaling efforts while at TRI. I'll briefly mention Droid, which came out last year at RSS. It's a very large robot data set. We went out to Airbnbs and we collected a bunch of data across very many different environments, many different rooms in these houses, many different tasks. And this is a collaboration amongst 13 different institutions, so it was a fairly large effort. With that, and the theme of this workshop, I'm going to focus on policy evaluation and failure detection bits. So before we begin, I want to motivate each of these directions a little bit more. And so starting with policy evaluation, most of the time when we see a paper in robot learning, we see tables like on the right? We see some success rates, we see some baselines, and hopefully whatever method's being presented is higher than the baselines. Problem is robot evaluation, real world robot evaluation is very expensive, right? So we're limited in how many trials we can do, which means very often papers put out, 10 trials. Is that enough? Is that sufficient? Can we actually differentiate between different policies at 10 trials? Also, there's these weird things with robot learning where the performance can vary across a number of different factors. So this example, we took a tier eye. So this is the in distribution version of towel folding. We have a red towel, you fold it, and you put it to the side. This is with the lights off, but obviously you can still see what's going on as a person. Completely breaks the policy, doesn't work. This is with a new towel that has never been seen during the demonstrations. So it's not in the training data. Works just fine. Doesn't care, right? So there are these weird things that maybe you can reason through in hindsight, but you can't always predict. So figuring out how these different factors affect the policy is challenging, right? Thinking about the different platforms, environments, tasks, lighting, like shown here, camera angles can affect things a lot, manipulants, so on. Okay, so that's the evaluation side. With the failure detection side, I like to preempt two questions that I've gotten while trying to pursue this failure detection direction. And I think they're valid questions, but I'd like to address them now. So the first one is it too early for failure detection? As in, we still need our robot learning models to work better. Why focus on detecting their failures when they can still fail fairly often? Well, we can actually use failure detection now to figure out what data we want to collect, right? So if we're seeing certain failures along a certain axes of things that we can change, for example, lighting, we can adapt and we can add lighting changes to our data set and actually make the policy more robust from identifying these failures. Another bit is we can learn and adapt from these failures, maybe online, maybe offline, to actually just improve model performance as we go on. That's one side of the coin. The other bit is, will failure detection become obsolete as we scale data, right? So at some point, we're just going to have so much data that our policies are going to be at near 100% success rate. And why do we need failure detection at that point, right? Well, no matter how much data you have, the system will eventually run into a failure. This is unfortunately what, deployment in human environments looks like, and deployment in general. And the system should be able to handle those failures gracefully and safely. So my argument here is that we're going to need failure detection on both ends of the development of these robot learning policies. And there's kind of no way to get around from it. All right, so with that, let's talk about some solutions, not just problems. So let's start with policy evaluation. All right, so the question we wanted to answer here is, does a learned policy generalize to the new environment? And here we're looking at an example diffusion policy doing a simple square task, right? And some of the things I mentioned that we can change are lighting, camera pose, object colors, object types, all these things, right? And maybe this looks like something like this. So in this case, we changed the color of the square that's being put on the peg to green, which was not seen during training, or to this light brown shade instead of this darker brown shade. What's interesting here is that the green works perfectly fine, and the lighter brown shade completely breaks the policy. Okay, so a basic approach, or a very common approach to how folks would evaluate things right now, is something like do 10 rollouts of the robot policy. Notice that we have 7 successes out of these 10 trials, and then report, hey, our success rate was 70%. What we'd like to do is just a little bit more nuanced. So the new statistical approach that we present is, instead of saying, hey, our policy is at 70% success rate, we will say something like, we are 95% confident that the success rate is at least, say, 46% here, and it has an average excess length of less than 26%. So that average excess length is how loose our estimate is. Okay, everyone with me so far? I'm watching for nods. Okay, great. All right, so this is a paper that was led out by Joe Vincent. He was our intern 2 summers ago. We're actually on our 3rd intern season at this point. And this paper was accepted into REL in 2024 and is actually going to be presented at ICRA this year. So come check it out if you'd like. The objective that Joe had was to provide generalization guarantees for the learned policies that will hopefully allow us to rigorously determine how well a policy performs in a new environment. There are some challenges with this, some of which I've already mentioned, but the policy networks can be very large. Generative policies are stochastic. We usually don't have a mathematical model of the environment, and these policies are quite often visual motor, so just taking in images. We want to minimize the testing costs in the new environment because, as I mentioned, robot evaluation on hardware is very expensive. So first off, how do we measure performance? What is success here? Well, one option is binary success failure metrics, right? Then the policy performance is a Bernoulli random variable, and we can lower bound our success probability. The other option is that we have a continuous reward. So then the policy performance is a random variable of some unknown distribution. And here, Joe figured out that you can actually upper bound the cumulative density function, or CDF. Why? Okay, let's take a look at it. So if we have our reward on the x-axis, we can see that for this green curve, a lot of the density is in the higher reward region. So this curve is better, quote unquote. Whereas this red curve has a lot of density in this low reward region. And so that curve is worse. So worse performance is higher CDF curve. So we want to upper bound the CDF. It won't go higher than this. Great. So I'm not going to get into the math of this, but at a high level, we want to find a lower confidence bound for the probability of success that optimally trades off between 3 things. The first is coverage probability. This is the idea that our lower bound, P bar, is actually less than the true probability of success, if we're thinking about the binary side of things, right? So this is a true lower bound. This is the first bit. The second bit is the excess length, which is how far our lower bound is from the true unknown probability. And we want this to be as small as possible because if it's too loose, the lower bound stops being useful, right? If we say the performance is better than 0% success rate, not super useful, but is technically a lower bound. And the last bit is this efficiency side of things, right? We want to minimize the number of samples that we need to estimate this lower bound efficiently. And so Joe came up with this software package where essentially all you need to do is you need to collect your trajectories for however many you have. This works particularly well at low data regimes. So thinking about 50 or less rollouts, you really see benefits in Joe's method. And you need to collect your however many successes you get in those N rollouts. Then you set your error tolerance, say alpha of 5%, that's a very standard choice. And then you can call his confidence interval function, which gets you the lower bound and that looseness, maximum expected shortage. And yeah, that's all you really need to do. What does this look like in practice? Well, remember that example where we had the square change color, and for example, we change it to green at test time. Again, this has never been seen during training, and we do 50 rollouts. We observe an 88% success rate, so that's normally what would be reported. But with Joe's method, what we can now say is with 95% confidence, that's that alpha of 5, the success rate is at least 79% with an average excess length of 12%. So we have 12% of looseness there. What's nice though now is people who are deciding on whether something is ready for deployment, for example, can decide whether at least 79% success rate is good enough. Maybe not. Maybe you need to go back to the drawing board and rework your system, get more data, whatever it is, to get a better lower bound on your success rate, but this gets you a guarantee. Same idea if we have the tan square. This one really fails, and you can see that in the videos, really is not doing great. So here, with 95% confidence, we can say that our success rate is at least 10%. That's probably no good for pretty much any application. We can do the exact same thing on the continuous side. What you can see here is that this CDF for the reward is quite nice. It's quite low. And this is our upper bound. So clearly, this is a good performing policy. Whereas for the square, it's quite high. And so our upper bound is very high. And so this performance not so good. We also tested this out on hardware. Here, the task is pour ice from a mug. The mug is red. So on the left side, we added some distractors that were benign, and the policy still worked fairly well. And it ended up with a lower confidence bound of 64% in the left case out of 50 trials again. And then on the right side, we have a harmful out of distribution environment. And what that means is we added a distractor that's red. So this red coaster, whatever that is, was added to the scene, and that actually affected the policy quite a bit because now it has confusion between what's the mug and what's not. And so our lower confidence bound ended up being 3.5% success rate. And that's, again, not so good. Okay, great. And then the last bit that Joe explored with this work is policy comparison. So far we've been talking about estimating the success rate for a particular policy, but very often in robotics, we want to compare different policies. And one thing you can do is if the intervals are disjoint, you can say that two policies are separated. So if two lower bounds are disjoint, we can separate the two different approaches. And here we did this with RT2, and we can see that what they reported in the paper, in fact, matches with our expectations, and the intervals between the two approaches are disjoint and happy. So you can see a difference between the two policies. Okay, great. So wrapping that up, the takeaways here are Joe provided us a generalization guarantee for imitation learning policies that you can use when the policy is deployed in a new environment, one that hasn't been seen during training. Why would you care about this? Well, it's a rigorous means to decide if the current policy in its current state is deployable and which policy is statistically better. And the last one is it can actually tell you how many trials you need to be some % confident in your results. So you can use it to decide on your experiment, which is great as well. If you'd like to check out the paper, it's here. And once again, it'll be presented at ICRA this year. Okay. Now for policy comparison, the question is, can we actually do better? So Joe's method really focused on estimating the success rate and the lower bounds for that success rate for individuals. Success rate of the baseline, the true success rate of the new policy, whatever method you're presenting, and whether the new policy is better than the baseline, right? So you might have this situation here on the right where your new policy has a confidence interval that severely overlaps with this baseline policy. If they're disjoint, then you're good. The two policies are different. But what if they are not disjoint and there's overlap? Well, there's this paper that came out and fairly long time ago now, 2016, but they make a very important point. If two confidence intervals overlap, the difference between these two estimates doesn't actually mean that it's not significant. And you can actually have policy separation in terms of comparison, even if the individual confidence intervals overlap. And this is really important because it basically means we don't need to be quite as pessimistic as we think we do. This is the idea of A/B testing, which optimizes only for the comparison. It's answering the question, is our new policy better than the baseline? And this can actually be more efficient because you don't have to simultaneously estimate the true success rates of both policies. Okay, so setting up the problem of A/B testing, we have T, which is our test statistic, which is looking at the difference between two means from one new policy and one baseline. And then our goal is actually to find a decision function that goes from this test statistic to a decision. And the decision options are, one, the null hypothesis, which means that our baseline P0 is actually better than our new policy P1. We don't like this hypothesis, but we have to consider it. And the alternative hypothesis is that our new policy P1 is better than our baseline, which is P0. Okay, then within A/B testing, there are two types of errors that we really want to think about. So one is the false positive rate. This is type 1 error. So this is the idea that in actuality, our baseline is better than our new policy, but we say that, hey, our new policy is better. So that's incorrect, and we don't want to be doing that. So we want to control for that. The other side of the coin is statistical power. We want that whenever our new policy is actually better than the baseline, we flag that and we say, hey, new policy is better, you're good. The higher this is, the more powerful the test. Great. And so, to summarize that, hypothesis tests are designed to guarantee that the false positive rate or the type 1 error is less than some value that you set as the designer of the experiment, and this value is alpha. The statistical power depends on the choice of the test that you use, and the higher the statistical power, the better it is. There's this idea of batch testing that's pretty common in statistics, for example, Barnard's test. The issue with batch testing is that you need to know N ahead of time. So N is the number of rollouts. So for example, 50 rollouts is how many you're going to do in the experiment. And you can't change afterwards. You can't reuse the data for, say, you do 50 rollouts, and then you want to add 10. You can't reuse that data. You have to start over. So what does this look like? Well, what if we have N trials? You know, we compare two different policies, we run them for N trials, but we actually don't find any separation yet. But we have more budget, and then we can start over, right? And so we have to throw out all this work that we did running these rollouts and start again with a bigger budget. So a lot of wasted effort. On the flip side, what if we go for a really large number of rollouts and we do get separation? But then we maybe wasted half of the rollouts. We wasted time, right? We could have stopped way earlier, but we continued because we had to set our N ahead of time. So this is where David Snyder's work came in. He was Haruki's intern last summer. And this paper will be presented at RSS in June, if you will be there. So the idea here is to do sequential testing. And they call it sequential testing for efficient policy comparisons, STEP. The goals are we control the false positive rate, like we talked about, throughout the whole decision-making process. And we want to stop as quickly as possible, right? So we don't want to waste trials as much as is possible. So we start with one trial. We don't have separation, right? We got 2 failures. We continue. We do a second trial. We see 1 success, continue. And then at some point we stop. Hey, we found pi 1, which is our new policy, is actually better than pi 0. So we take the alternate hypothesis and we accept that one. Great, everything's good. And we stop. So how does this work at a high level? Well, our decision set is actually three different things. So it's the null hypothesis that the baseline is better than the new policy, the alternate hypothesis that the new policy is better than the baseline, and we don't have we have not enough data, right? So you have to keep running it, and you can decide whether you have enough budget to keep running or not. And then we have the decision rule that goes from the number of successes we've observed for both policies and how many samples we have to one of these decision points. And we only stop if the answer is not insufficient data. If it's insufficient data, you continue. So the objective looks kind of like this. And if you read the paper, David actually ends up with a linear program at the end of this, which is great for optimization purposes. But what do we have? We want our process to stop as quickly as possible. So the number of trials at which we stop should be as small as possible. So we want to minimize that. And we want to maximize our statistical power. So how correct our method is. And we want to balance safety, right? So we don't want to say that our new policy is better when it's not actually. One last thing to mention here is that we do need to choose a maximum number of N that we would ever consider. So this is your largest budget. Of course, as you make this super, super large, you're going to lose some statistical power, but it can be actually pretty loose, which we'll see in the results in a second. Okay. So with this, David ran some experiments. Here's a fold towel experiment. We've seen this for a second before. So the idea here is, sorry, I just restarted it. The idea here is we have two policies and they can be at two different empirical success rates, right? So one, the baseline is at about 56% and the new policy is at about 92%. Our false positive rate that we want to control for is 5%, which is pretty standard. And we're looking at different budgets here. So we can have a maximum number of rollouts at 50 or a maximum number of rollouts at 200. And you can see between these two lines the inefficiencies, which are actually quite low between the different methods. So SAVI and LI are baseline sequential methods. STEP is our proposed, and SPRT is actually an oracle. N is the batch number that we chose fairly arbitrarily, but that's sort of a reasonable amount for how many rollouts you're going to run. What you can see is that all the sequential methods can do this faster, right? And if you had chosen a batch number of, say, 10 instead of 50, you would have ended up with no decision and had to start again and throw those 10 out and go again. So the nice thing about the sequential testing is that it can actually just stop early and you don't need to think so much about your N. Between your N max, you can see that for the sequential methods, there's actually not that much that we lose. It's a couple trials. So you can be fairly not conservative with your N max and make it relatively large. I'm going to keep playing this video. I talked through a lot of these things. Great. So in this stack cube, what's important to notice is the two policies are actually very close together in empirical success rate. So we have one that's basically not working at all and one that's working at 3% success rate. What's nice is that David's method STEP can actually get very low numbers here compared to the other two sequential tests. So you can save some amount of time. And this is quite a large saving, right? Compared to LI, that's nearly twice, which is awesome. And the ability to differentiate at very close success rates is actually really important because that does happen a lot in reality. Okay, so what are our takeaways here? We have a framework for providing efficient sequential policy comparison for imitation learning policies with statistical guarantees. Why care? Well, STEP minimizes the number of rollouts you need to policy separation, and researchers can look at the results and decide whether to continue evaluations mid-process or not. So with that, let's move on to failure detection mitigation. So I'm running a little bit low on time. I think we started about 5 minutes late, so I can go 5 minutes late as well. I'm gonna assume I can, unless I'm told otherwise. But okay, failure detection. Great. The difference between failure detection and evaluation is a little bit subtle. So evaluation, we saw these batch rollouts or these sequential rollouts, but you're looking at a bunch of different rollouts regardless, right? Whereas in failure detection, you're actually looking at within a rollout. Can we identify when the robot, for example, was trying to pick something up and ended up going upwards instead, right? That's a problem. That's a failure. We want to flag that to the operators. I kind of talked about this already, but failure detection is important for things like safety monitoring, targeted data collection, recovery, and it gives us the ability to learn and adapt from these failures that we identify. And I've said this before, but I really do believe in this, that regardless of the training data amount, failures will always be present. The system should be able to handle those failures gracefully and safely, either autonomously or with humans in the loop. So why is failure detection difficult? Well, there are a lot of different ways that policies can fail. And this is a very simple simulation setup from RoboMimic, right? The square task. But there are already so many different ways in which the policy fails. For example, in the middle one here, it never picks up the square. And some of them, it drops it in the middle. All these different times and ways in which the policy fails. It's also not super clear what signals are actually most indicative of failure. So should we be looking at action data? So this is X and Y here for predicted action in a diffusion policy. And there's some differences between the red failures and the blue successes, but it's not super clear exactly what signals we should use here. Plus, these policies are usually visual motor, right? So we have images to look at. So are these observations actually where we should be pulling our signals from? Is it a combination of both things? And then the other bit that I think causes a lot of confusion often is what is the connection between what is out of distribution and failure detection? So out of distribution detection comes from computer vision, comes from machine learning, and thinking about looking at images. And for example, we have a robot that was trained with green walls around, and now we have a robot that's deployed in an orange room. Failure detection, on the other hand, doesn't really care if it's a green or orange room. It cares whether the robot can do the task. So, for example, if the robot succeeds in the out of distribution orange room, then great, nothing should flag. Versus if it's in the in distribution green room and something went wrong, it should flag, hey, there's a failure. And this actually happens in real life. So this is a coffee cleanup skill task. Here we have a green towel that the policy didn't see during training time, and here we have a white towel that it did. And it fails to pick up the mug, which is part of the task in the in-distribution environment, and it succeeds at cleaning up the spill in the out-of-distribution environment. So then failure detection is actually just out-of-distribution detection in successful policy space. This brings us to the next paper. This was work by my intern last summer, Chen Zhu. Can we detect failures without failure data? And this will also be presented at RSS in June. The idea here is Chen took basically the inputs to whatever imitation learning policy for us, diffusion policy, for example. We have these camera images, they're passed into a feature extractor. And they're combined with robot states to form observations. We can optionally add action predictions as input here and come up with a scalar score. And the scalar score is what we learn, and that's our failure detector. The important bit here is that the feature extractor is trained with the policy in the loop. And so that gives us information about what would actually matter in terms of features for the policy. And so that's what the failure detector should actually pay attention to. All right, so that was stage one. Stage two is we calibrate our threshold. So what we want to do is we want to get some successful rollouts. And then we want to find a calibration threshold with some statistical guarantees that tells us when to actually flag failure. And then the full system ends up looking like this, where we have some successes that should be below this threshold and a failure when it leaves. That's when we flag, hey, there's a failure. There are a couple assumptions that we make for failure detection. The first is that training demonstrations are the same as for the learned policy. So whatever data you have for imitation learning, that's what fail detect is going to use to train. Then we use our learned feature output, so a ResNet, clip encoding, whatever it is that the imitation learning policy uses as input to our score network. And lastly, we need successful rollouts set aside for calibration of our score. Importantly, we only wanted to consider success data here. We didn't want to have access to any failure data for training the score. And as such, the reason being is if you include failure data, you have to think about overfitting to different failures that you observed. And we wanted to actually focus on just estimating the success distribution. Chen spent a lot of time trying out many different methods. Some of these were post hoc, so you actually didn't need to train anything. Some of these were learned, like sort of what I mentioned just now. And the one that worked best for him is one that he designed, which is called log-PZO. And it's based on flow matching. Sorry, I'm starting to lose my voice, which is why I'm slowing down a little bit. But it's based on flow matching, and it's thinking about the distance between, or a mapping between, observation encodings, OT, and latent standard Gaussian noise, Z. And the idea is we learn this network that gets us this difference between the two. And this OT is actually an interpolation from OT all the way to Z, where S goes from 0 to 1. And what we can then do is if we have a new observation OT prime, we can rearrange this equation and we can get this ZOT prime. And because ZOT prime is approximately standard Gaussian, we can actually get the log likelihood here. And if we simplify this equation, it's proportional to just this distance, this norm, L2 norm of the ZOT prime, which is just the latent. And we can actually use that as our learned failure score. So the higher this number, the lower the likelihood, and so that means failure. Yeah, so we just talked about this. log-PZO estimates the likelihood of a policy-aware latent embedding, lower likelihood, out of distribution, so failure. The main bit that I want to get across is that it's really important to have this feature extractor be policy aware. That's how it has an idea of not just orange versus green room is important, but how well the policy is doing and what the policy is paying attention to is useful. And then the calibration is done from successful policy rollouts. So that's another signal from the policy to tell us how to detect these failures. I'm not going to talk too much about the score calibration, but essentially we use conformal prediction and we create a band here that tells us what is likely to be a successful rollout versus not. When the score leaves the band, that's when we flag failure. I will skip over some things in the interest of time. Chen did 1 million experiments, and the takeaways were learned methods worked better than the post hoc ones. Stack from Marco Pavone's group, Marco speaking later in the workshop, I believe. Stack is a post hoc method, so nothing had to be learned. And the learned failure detection scores actually did a bit better there. There are some trade-offs. You have to learn a model versus not having to. But if you need the performance, then learned methods seem to do better. The other bit is post hoc methods often have to sample in order to compute a failure score. And that slows them down. So we actually couldn't run Stack on our hardware because that would have been too slow. Similarly, for hardware experiments, he had very similar takeaways. Learned methods were more robust than the post hoc ones. And I'm going to skip over this to show some videos because I think that's probably the most exciting part, and I'll end there. So these are some simulations. RoboMimic, the square task that we've been talking about quite a bit. That's what the success looks like, and so that's fairly straightforward. And here we have a failure, and as soon as it slips, we flag failure. That's the red border. So this is a success for a transport task. We hand over the hammer after opening the lid. Great, right? And then here we have a failure for that same transport task. And what you see here is it actually throws the lid. And as soon as it throws the lid, it flags failure. So that's great to see. And here we have a hanging task from RoboMimic. So it hangs all the tools. And this is a failure. It missed that hang, and as soon as it missed that hang, it flags failure as well. So it does seem to be responding quite well to simulation, but what's obviously more interesting is how it looks like on the real world. So this is the towel folding task that we've seen a couple times already. Folds once, folds a second time. And not the most beautiful fold, but it puts it away. Great. So the failure case, here there's an adversarial human trying to mess with the robot and be annoying. And so it's doing everything, everything's okay. And then the human comes in and moves it, and things break. And it starts to fail, fails at this fold, and the failure detector flags as well. Here we have a distractor we hadn't seen and a low data regime in this pretty extreme crumpling of the towel to start. But it can succeed at this task. You know, it can fold it away. And then when it fails in this out of distribution setting, it looks like this. So it tries to straighten it out. And it misses that corner, failure. So it's really cool to see that it actually is fairly robust to different settings. I'll show one more task. Maybe we'll start here. So this is the coffee spill cleanup task. This towel is amazing. Look at how well it's done. And then this is yeah, sounds good. I will stop right after this. So this is a failure case where it missed the mug, and so we right away flag failure. And then last couple videos I'll show together. Maybe we can just watch them all at once. There we go. So this is an out of distribution scenario where it can clean up the spill, but here, this situation where it would actually end up having the gripper in the liquid, that's the dangerous case where these automated failure detectors is actually what you want. You want to be able to flag failure when it would be system critical, right? It could ruin the robot. So with that, this is the failure detection work. We learn a score, we calibrate a threshold, and then we have an online failure detector. And if you'd like to check out the paper, it's here. And this is our focus. And with that, thank you.